Hello everyone, my name is Amin, and today with Gizem, we are going to present our paper, Find the Funding, Entity Linking with Incomplete Funding Knowledge Bases. We have written this paper with Georgios Tsatsaronis from Elsevier and Faegheh Hasibi from Radboud University. The main goal of this work is to extract the funding information from the text of scientific papers and link it to Crossref taxonomy, which is the knowledge base of all funders. This is an open access taxonomy and everybody can access it. Let's have a look at Scopus, a product of Elsevier, which indexes all papers published by different publishers and presents the title, abstract, citation, and some metrics and metadata of articles to the researchers. Let's look at an example on Scopus. As you see, it shows different information about the paper, like the title, authors, the affiliation of the authors, and some other metrics and metadata, including funding details. In this part, as you see, it shows part of the paper which talks about the funding information, and in addition to extracting the funding information from the paper, it also links it to the taxonomy and shows us some information about the funder, like the acronym, and also it links to the website of the funder. But why this information is valuable for scientific community? First of all, it enables the researchers to find out which funders in their region or country are active in their specific domain. Suppose you are a scientist wants to start a new research and looking for funding. You can use this capability of Scopus to figure out which funders might fund your research. Also, this helps funders to understand the impact of their funded researches. They can check if they are funding the right researchers, and also they can measure and track their outcomes. To train and evaluate machine learning models to extract and link the funding information, a goal set is created. Let's look at one example. What you see is the plain text of an article annotated by an expert. As you see, he has highlighted the snippets talking about funding information, and also the funding organizations are annotated. For each funding organization, it is linked to the Crossref taxonomy by its funder ID. To have a high quality data set, each document is annotated by two and harmonized by a third independent expert. The collected goal set is released alongside the paper. Each document in the dataset is in a JSON format, which shows the sentences talking about funding information, plus annotated organizations and their funder IDs.
Thank you, Amin. First, I'd like to mention additional challenges entity linking brings in real-world applications. For example, there is usually a limited amount of training data and computational power. There are also knowledge base related challenges. For funding domain, the knowledge base is sparse, it's incomplete, and it contains only brief information such as the name and the country of the organizations. Because of the sparsity, we can't utilize graph-based solutions. Recently, there had been a lot of advancements for entity linking, both in zero-shot and open domain settings. We can't use the approaches proposed in zero-shot setting, as the work doesn't address the problem of out of knowledge-based entities. And the models proposed in open domain entity linking rely on rich relations and descriptions that we don't have. In our approach, we use separate models for mention detection and entity disambiguation. For mention detection, we use a BERT model and we perform task adaptive pre-training to obtain BERT tabbed. We do this by training the BERT model with the mask language modeling objective using acknowledgement sections of academic articles. Later on, we fine-tune the BERT model on an annotated dataset for the mention detection task, and we obtain our final model, BERT-MD. Our entity disambiguation model fund consists of two steps, a candidate entity selector and an entity ORNL selector. For candidate entity selection, we use a bioencoder model that tells us the likelihood of an entity being the target link of a mention. The bioencoder uses two BERT tapped models, one for encoding the mention and the other for encoding the entity. The mention encoder, as you can see from the left-hand side, uses both the mention and its context to generate a mention representation. The entity encoder, which is on the right-hand side, generates the entity representations using different attributes of the entity. In this work, we use two attributes. One is the name of the organization, which is a multi-valued field, and the other is the country of the organization. Here in the example, as you can see, the funder has two different names that it can be referred to with. One is National Science Foundation, and the other one is NSF, an acronym. And we also can see that the funder organization is from the United States. The representations are said to be the vectors corresponding to the CLS tokens of the BERT models. After the representations are obtained, the likelihood score is calculated by performing element-wise multiplication on these representations, weighted by learnable weights W. After the candidate entities are obtained, we make use of a small gradient boosting machine for mapping each mention either to an entity in the knowledge base or to nil. This model uses 5 lightweight features based on string similarity and statistics. A mention is linked to the entity with the highest score if the score is higher than the threshold. To train the bioencoder, we make use of binary cross-entropy loss. Following the DEAR architecture proposed by Gillick et al., we do the training in rounds using both random and hard negatives. Hard negatives are extracted each round using the model learned in the previous round. We define the hard negatives as entities ranked above the correct one, and for the out-of-knowledge base cases, we select the top 10 entities. However, unlike DEAR, we don't use in-batch random negatives, as it provides less diversity due to the sparsity of the entities. We observe that with in-batch random negatives, same subset of entities appear repeatedly, and that's why, instead, we sample the random negatives from the knowledge base. In each round, we sample random negatives proportional to the total number of hard negatives. This way, we form a balance between hard and random negatives while giving more hard negatives to the mentions that need it. We evaluate our approach in 3 different settings: mention detection, entity disambiguation, and end-to-end entity linking. For mention detection, we can see that our model outperforms the other approaches in terms of F1 score. The performance difference between Stanford and NER and our model is very large. When we compare our model to FLAIR, we can see that our model has higher recall, while FLAIR has higher precision. Lastly, we show the effectiveness of task adaptive pre-training by comparing our model to a BERT model that is only fine-tuned for the mention detection task. As for entity disambiguation, our model fund outperforms the commonest baseline in terms of accuracy and performs close to GBM F26, which is a gradient boosting machine with 26 handcrafted features. However, fund is more efficient than GBM F26 because the computation of the handcrafted features are very expensive. Fund is 10 times faster with GPU and 3 times faster without GPU compared to GBM F26. In addition to these baselines, we also implemented Blink's bioencoder with a score threshold, and we obtained an accuracy of 60.16, which is far worse than the other methods. Lastly, we report our model's performance on end-to-end entity linking, showing that this approach can successfully be applied to funding domain. We obtain a micro-averaged F1 score of 75.81 and a macro-averaged F1 score of 76.59. To conclude, with this paper, we have proposed a data-efficient model for entity linking. We improved upon existing entity linking approaches for funding organization, and release new training and evaluation data sets for entity linking in funding domain. And that's it. Thank you for listening.